This is part of the work that we did in a large project with industry collaboration that was actually going on for the last 7 years in Vienna, which is called this Christian Doppler Laboratory for Artificial Intelligence and Optimization for Planning and Scheduling. And there we collaborated with 3 different industry partners in the area of scheduling, in the area of production scheduling, of test laboratory scheduling, and of employee scheduling. In this project, we dealt with different problems and with different solution methods. And today I want to focus on hyper-heuristics, so a very problem-independent solution method that we investigated, and in particular, what we did there with reinforcement learning. And I also want to show the application of these methods on some of our industrial scheduling problems that are hopefully of interest to you. So this is work done in collaboration with Nusret Muslio, who was the leader of this laboratory and also my PhD advisor. And parts of this work have also been done by a master student of ours, Hannes Meyerhofer. So basically, my research interests are mainly in the area of these complex real-life scheduling problems. And in this project in particular, the focus was on these employee scheduling problems. And they are not just the optimization of a pure cost objective, but actually very much in combination with employee satisfaction objectives, which is also an important goal of the company we've been working with to create basically these schedules that combine these two as well as possible. This often creates some very challenging problems where we have multiple goals, and those are often conflicting, and those are often very non-stationary. They change over time, they change between different customers, and this makes it often very challenging to even find a problem formulation that everyone agrees on and to agree on the optimization goals that we want to solve. Regarding the methods, we are quite flexible in the methods that we use. So we've been working with exact methods like CP, and now I'm also currently at Monash for 2 months diving deeper into the topic of CP solvers actually. We've used MIP solvers, we've developed a branch and price approach. We are often for the larger problems using meta-heuristics like simulated annealing and taboo search. And for the practical applications, often the best solution methods are then some kind of large neighborhood search where we solve some sub-problems exactly or close to optimality. And then in the larger context, the question is how to select those sub-problems efficiently. But what I'm going to talk about today is a more problem-independent view called hyper-heuristics. And I'm going to talk about more details what hyper-heuristics exactly are and why they are useful in this context of very diverse and changing problem definitions. And we're also investigating learning in optimization. In this particular instance today, I'm going to talk about reinforcement learning to take small heuristic building blocks and assemble them using reinforcement learning to meaningful combinations. And finally, we've got a large range of methods, and naturally, we want to analyze their strengths and weaknesses. And for this, we often use instance space analysis. And this is also where the collaboration with Kate comes in, and where we've collaborated by now on several different problems and using instance space analysis on them. I'm going to talk about the industrial problems a bit later in more detail. But for now, just as the motivation why we even want these hyper-heuristics, I want to show you just a brief overview. So we've got these kind of rostering problems like rotating workforce scheduling. I should probably point with the mouse here so that people online also see it, where basically you already have shifts and you want to somehow assign the employees to those shifts according to several different rules. We have several problems where we actually do not yet have the shifts, but we have some kind of demand, for example, given for each time of the day, or bus driver scheduling has already been mentioned where the vehicle schedules are already done, but we now want to assign the employee duties to cover this demand as well as possible. And also a new recent problem is in aircraft maintenance routing, where we've also started a collaboration with Peter. where we want to assign aircraft, so specific aircraft, to the already scheduled flights in a way such that the maintenance that also needs to be scheduled is distributed in an even way. So it's just a brief overview of the kinds of problems we're dealing with. And so we are working with this company Ximes, who do basically software and consulting. And then their customers have these various scheduling problems. And as all of you who work with industrial problems know, they come with a lot of complexity. The requirements are often not clear, like you come up with some problem definition, you give them a solution, and they're like, no, actually, you haven't done this constraints that we've never told you, and this objective should be different, and so on. So it's really changing quite a lot. For example, bus driver scheduling, there's a collective agreement for Austria, but not even all companies use the same collective agreement. Some have their own company agreements. Then they want to explore different directions where they say, okay, what if we change these rules? How would this affect our schedules, and so on? And we have some very good methods that are problem specific. For example, I mentioned branch and price. For small to mid-scale bus driver scheduling instances, this gives us near optimal solutions. Great. But if we want to adapt this to new rule sets, this is very challenging, because there we have the sub-problem, which is a resource constraint shortest path problem. And there we need to put new constraints into the sub-problem, and then this makes things very hard to adapt. So what I'm going to talk about in this talk is the complete opposite. We want a method that knows nothing about the problem, but still can adapt on the fly to an instance of a basically unknown problem. And this is what hyper-heuristics have basically been invented for. So the core concept of hyper-heuristics is you have this notion of a domain barrier. You don't need to know a lot about the problem domain that you're applying to. So in this problem domain, you've got your representation and so on that the hyper-heuristic doesn't even need to know about. What you need to know about is you've got an evaluation function that returns the current value of the objective function. And what you have is this heuristic repository. So in this, for example, you have several local search operators that can only improve the solution or keep it at the same objective level. This can be some simple hill climbers, can be some exhaustive search, can be some randomized hill climbers, different simple local search operators. You've got mutation operators that can change something in a solution in an arbitrary way, like some short random walk or some other simple mutations. You can also have crossovers that combine different solutions. However, we don't use them in our real-life domains, but in the general framework, that's also possible. And we have some destroy and repair operators that take one part of a solution and replace it by something else. And now what the hyper-heuristic knows is how many of these heuristic building blocks do we have. These are the so-called low-level heuristics. And of which type are they? And then it can choose to apply one of them. And then it just gets back, how did the objective change? And how long did this take? This is not much information to go on. But the advantage is if we have a hyper-heuristic that works reasonably well on different domains, we don't care if the problem changes. Okay, then we include a new constraint somewhere down here. But our methods, our solution methods does not need to change. Instead, we build it to just work on this limited information that we have. Now, what can you do with this limited information that you have? Well, at least you can figure out, for example, if the objective does not improve over some time, then we are in a local optimum probably. So we want to do something that is more like mutations, destroy and repair that gets us out of this local optimum. While, for example, if we can see frequent improvements in the objective, maybe it's a good idea to just do several steps of local search to exploit this situation where we're currently in. And ultimately, the idea is that we want to learn some useful chains. Like if we're stuck, then it's probably good to do mutation heuristic 2 followed by local search 1 and then local search 3. Maybe this is a good strategy. And ideally, we want to learn these strategies over time. Now, when you look at reinforcement learning, then this core loop of reinforcement learning actually looks a lot like this core loop of hyper-heuristics. Because you've got an agent, which is the hyper-heuristic, that does an action, which is selecting the next low-level heuristic to apply on an environment, which is the problem domain. And then the state of this environment changes. So we change something in the solution, and you get back a reward, which is somehow related to the change in objective and the time you need it. So this is kind of a good natural fit of this loop. With the main issue that actually you really don't know a lot about the state. So you only get these changes in objective function. You don't know how the state of the solution actually changed. And that's why previously in literature, there were mainly some very simple state representations for these hyper-heuristics. So like, what was the last heuristic that was applied, or maybe a few of them, and what was the last change, or maybe the total change, something like this. But actually, we thought that maybe we can improve this. I mean, we still have the whole trajectory of this search overall. So we can get some more features of this trajectory, hopefully, and use them to get a better idea of the current state of the search. And this is why we introduced this new hyper-heuristic, which we called large state reinforcement learning. So you can think about the features of this search trajectory.
Hello, Moto.
You can think about all the features that you want to use. We still want to have a reasonable number of features that we can do this very fast, because we always want to learn online while we are solving the instance. The classically already existing ones were something like last heuristic, type of last heuristic, the sign of the last change, the magnitude of the last change. But you can, I will talk in a moment about solution chains, like we have certain chains, and then if we have no improvement, we reset back to the best solution. So you can track how far are you through the current chain. For example, at the beginning of the chain, you might want to diversify and then later to intensify. You can track like the number of steps since the last improvement, the number of steps in total, that the time that you took so far, how the objective changed, not only since the initial solution, but for example, since the best solution you ever found, since the last time you reset to the best solution, and so on. And we do not want these features only for the whole trajectory, but we also want them for like the most recent part of the trajectory. So for example, for the last 10 or last 100 steps, we want, so then we have like features about the whole trajectory and about the more recent one. And then we can, for example, reason that in the more recent one, we had no improvements, but previously there were very strong improvements. So we're stuck in a local optima and so on. In his master thesis, Hannes has also looked in more detail onto these features and has analyzed in more details which of these features are more or less helpful on different domains. But I will not go too much into detail here. As I've mentioned, these changes are also important. So if you just always apply and apply, then maybe you had a best solution at one point, but you made one mistake going far away and then you're wherever. So periodically, we want to reset to the best solution. And based on a previous hyper-heuristic by Chang, the idea is to use the Luby sequence. So you have very often very short chains, and then exponentially less often exponentially longer chains. That's kind of the idea of this Luby sequence. And we additionally learn a novel multiplication factor for that. So for example, if we have a problem where like one is never going to do anything, we always need to combine at least 2 or 3 heuristics, then we learn this factor that we just multiply with all values of this sequence. We also do full resets if we're completely stuck, according to certain criteria, like 1,000 consecutive chains without any improvement, or 100, and we've used at least 1/10 of the total runtime if the heuristics are slower. And in the end, we jump to the best solution we had over all these resets, and then really try to intensify more in the very last part of our search. Now, the components we still need for reinforcement learning is we need a value function approximation. And again, we are doing this online. We often do not have a lot of time to do something very sophisticated. And it's also a very stochastic and noisy environment. So we actually want to do something simple. So we do a tile coding, which is basically a discretization because we have most of our features are like real numbers. So we do a discretization, but basically when you discretize, you have these arbitrary steps. So what tile coding does is it does multiple discretizations, which are all offset by a slight random factor to minimize the effect of these arbitrary steps. We need a reward. And the intuitive thing you might think would work well is that you just use the change in objective function. But actually it turns out that this didn't work well. For several reasons. For example, at the beginning, it's very easy to find improvements pretty much anywhere. And then later it gets very hard. So instead, what we give as a reward is like we give a positive reward if we have a new best solution. And this reward is scaled by a factor of how long we have not improved. So if we are already in a very good state of the solution, and it's very hard to find even better improvements, then it's worth more if we still find something. That's the idea. And in the end, we have a penalty for the runtime. So if it takes longer to find an improvement, then this is a penalty. As a learning agent, we use gradient descent Sarsa lambda, which is a standard learning agent where we've tuned parameters to those that you can see here. Policy is an interesting aspect. So we want to balance exploration and exploitation. And the standard kind of is the epsilon greedy policy. So with an epsilon of 0.1, you try something new. And with 0.9, you try the best that you've learned so far. But again, because we are in this online learning setting where we have a large number of potential combinations of low-level heuristics, but we are unlikely to find the good ones if we search completely randomly. And there are several hyper-heuristics that work very well that use some form of iterated local search. So what we do is we bias the exploration, and we're more likely to explore something like ILS. So diversification first and then intensification. We can still explore everything. So if this is not good, then eventually we will discover that. But it's just giving it a head start, basically, and giving it this bias. Yeah, and with these components, we evaluated this on this academic benchmark from this heuristic search competition in 2011. So basically, they had a competition for these hyper-heuristics with 6 benchmarking domains. One of them was Maxat, the bin packing, personal scheduling, flow shop, traveling salesperson, and vehicle routing. And the idea here is in each of the categories, you can get points. And then the one with the most points wins. And here we actually looked at the individual components or some of the core components of our hyper-heuristic. And it's quite interesting that if you just do ILS, basically without learning, but just this ILS biased randomized search, you can actually get quite far. For some of the domains, this is actually really good. However, there are also domains like bin packing where you don't get any points with just that. So it works on many domains, but on some of them not at all. And on some like Flowshop and TSB, it's not very good. On the other hand, if you do reinforcement learning without this ILS bias, then again, for many domains, this is perfectly fine. But for example, for this Maxat domain, we couldn't get any points. So we can see that it's really helpful to have this combination of these different aspects to maximize our performance. We also investigated if we just use a very simple state representation. Again, for several domains, this is enough, but there are also several domains where this is significantly below the result we get with the expanded states representation. And so the nice thing is if we combine all these things, then we're not at the very best result in every domain, but we are very close to the best result in every domain in this comparison. And so this shows that this is very general and can really adapt to the very different behaviors in the different domains, at least for this academic benchmark. We also compared to a lot of other hyper-heuristics on this benchmark, where in total, so there were 20 in the original competition, we've included several additional ones that outperformed the competition winners since then. So GIHH was the original competition winner, and we are very close to them on this benchmark, and we can outperform the other methods that also use reinforcement learning as their core method, which are like the QHH and RL, which are the next ones down here. There are some that are a lot better on this academic benchmark, especially ILS-based ones. But we will then see on the real-life domains, this does not necessarily mean that they are also perform that well on the real-life domains. And we are interested not only on this small benchmark. Basically, there you have just a few minutes for each instance. Heuristics that are very fast and much smaller scale than we have in our real-world application. But we were interested to use these methods on our real-world problems. And so we tested them on these 3 problems. Yeah, and I want to first give you a brief overview of what we want to achieve with these problems, and then show you the results of not only our hyper-heuristic, but also a range of others that we compared on these problems. So for rotating workforce scheduling, we assume that we already have some defined shifts, for example, a day shift, afternoon shift, and night shift. And for each of them, we have a given demand for each day of the week. This is a small toy example. We have a certain number of employees that we want to assign for a cyclic schedule. And then we have several regulations regarding these assignments. For example, 5 to 7 consecutive days of work, followed by 2 to 4 days of work, and so on. We also have these sequence constraints for each of the individual shift types. For example, for night shifts, we only want up to 3. And we have consecutive constraints, like after a night shift, you can't obviously immediately have a day shift because there would not be enough break in between. And then you can get a schedule like this. So for example, the first employee starts with a range of day shifts followed by night shifts, then continues in the next row, so 3 free days, next block, 3, next block, and then back to the beginning. So the idea is the employees start in different weeks, but they all rotate through the same schedule over the range of 4 weeks. Now, we do not just want a satisfying solution, but we also have several objectives. In this case, mainly regarding the weekends. So for example, we want to maximize the number of free weekends where the whole weekend is free. Or we want to minimize the maximum distance between free weekends, and also some other criteria in this direction. More recently, we've also experimented with even more objectives, like for example, a target length of consecutive shifts, not just the minimum and maximum, but we also want to minimize the deviation from a target length and others like this. For minimum shift design, the idea is that we have a demand for each time of the day, and we have some boundaries for our shifts. So for example, windows for shift start and length. And we want to now design shifts such that this demand is covered as well as possible, that we are within these bounds for the shifts, but also that we use few different shifts. And we usually have the demand not only just for 1 day, but for 1 week or even more. But we still would like to reuse the same shift times on each day to make it easier to handle for the employees, that they don't have very different shifts on each day. So for this very simple toy example, you can perfectly cover the demand with these 3 shift types. So one from 6 to 6 with 3 employees, from noon to midnight with 2, and 1 night shift with 1. But of course, in practice, we can't exactly cover the demand. So we want to minimize overcover and undercover, usually with different weights. Often it's preferable to have a few more employees than to not have enough employees. We want to minimize this number of different shifts, but we also, for example, want to have boundaries on the average length of shifts. Because you can imagine with short shifts, it's easy to cover these peaks, but then maybe you have all shifts are only 6 hours long, And then in the next step, you would like to assign them to full-time workers. So 40 hours per week, 6 hours per shift. That would mean, well, more than 6 days of work per week, which is not really a good idea. So we want to keep the average shift lengths in certain boundaries so that we can assign them properly in the next step. Bus driver scheduling, as already mentioned, we have vehicles where the vehicle tours throughout the day are already assigned. So in this small example, you can see 8 vehicles, and each of them has a certain number of bus legs. And between those bus legs, the driver could change or take a break if necessary. And some of them, for example, are only active during a morning peak, while others are active during the whole day. And so for each of these legs, we have a start and end time and also a start and end position because the buses move throughout the city. And we want to, again, generate shifts for the drivers according to a collective agreement that was made by people who did not think about how to generate these shifts. There are loads of different notions of time, like the actual driving time, working time, then there's rest breaks that are unpaid. And for example, the total duration of unpaid rest depends on whether a certain part of the rest is centered in the shift or not. It's all kinds of nasty things. In fact, so nasty that if you just put in the rules, how they are written in the collective agreement, put as objective cost and press enter, then you get something like this down here. And I guess even without knowing the rules in detail, you can see that this looks horrible. What we came up with together with the company was an objective function that gives us this as the optimal solution. And I mean, you can see immediately that this is probably way better than the previous one, but it took quite a long time to arrive at this objective function. And again, this is just for the general collective agreements without company-specific rules or wishes that frequently occur. So you can see we have problems that can become quite complex, that can include several different objectives that are also quite different in structure, like whether it's this rostering application or different ways to generate these shifts. And yet now we have this hyper-heuristic, and we want to apply the same hyper-heuristic without any further tuning or anything to these very different domains. So what are the things that we need to, that we are able to apply them? We need those low-level heuristics, but we can build them quite easily. We can just throw in some first improvement heuristics with different numbers of steps, best improvement, some randomized improvement with a certain number of iterations. And we have our local search heuristics. For the mutations, we can do some mutations that are more likely to improve actually. So like random improvement with Metropolis acceptance criterion at a fixed temperature. So always accepting improving moves, but with a certain probability also accepting worsening ones. And we can do some random walks that just change the solution arbitrarily. We can use these for all of the domains, but with different moves specific to the domain. So for example, if we think for bus driver scheduling, we can use a swap move, which just takes one bus leg, moves it to another employee. And if there's an overlap, then we move the overlapping ones back to the original one. And we can do this for not just one employee, but for different lengths of consecutive bus legs. We also have these destroy and repair heuristics. And for those, we used remove employee heuristic. So that just takes the whole employee, removes it, and then reassigns everything that was assigned to this employee, which has the potential to maybe completely get rid of this additional employee so not the employee himself, but the need for an additional employee in the solution, let's put it this way. And remove tour, where you just take one vehicle and remove all the duties that have some part of this vehicle and then try to reassign it. And with these building blocks, we can immediately apply the hyper-heuristics. So I'm now going to show a few results for each of the domains. So first for rotating workforce scheduling. Now, what do we see here? Now, down here, these are all the hyper-heuristics that we evaluated. I'm not going to talk too much about what they do. But basically at the end here, we have ours, last RL. In green, we have this original competition winner, GIHH, and the modified version LGIHH, which despite being now more than 10 years old, are still surprisingly competitive also on real-world examples. And we have in this magenta color these recent ILS-based heuristics that performed very well on this academic benchmark. And for rotating workforce scheduling, this is a more tightly constrained problem where it's often even hard to find a feasible solution. So that's why this graph shows the number of feasible solutions out of 100 that we got. And for each color, for each heuristic, there are 3 bars, which are 3 different objective versions that we tried to see if this makes a difference. Now, what can we see here? We can see that actually these GIHH versions win in this comparison, so they can find the most feasible solutions. And what's very interesting is that especially some of these ILS-based ones that actually won the academic benchmark, the small instances, does actually not generalize so well to this real-life scenario, and is among the poorest performances here, which is quite interesting. And we can see that our learning hyper-heuristic is on this plateau where actually for this problem, most of them are. Now, also as a comparison, what are we using here for the real-life applications? So actually, for most of them, we use CP here, which works well because this is a highly constrained problem, and so CP is quite strong in solving that. There is also a branch and cut approach, which can solve problems with very limited optimization objectives very, very fast, but is very hard to extend to more complex scenarios. Now, if we go to minimum shift design, so this is a problem where basically everything is feasible. It's just potentially very bad. Like even in this formulation of the problem, even an empty schedule is a feasible solution, but it's very bad because you have a lot of undercover. So what we show here in this graph is the comparison to the best among all hyper-heuristics. So for each instance, the best one has gap 0. And then for all the other methods, we show the percentage gap to the objective of the best one. And we can see here that our new learning hyper-heuristic can, in this case, outperform all the other hyper-heuristics in this comparison. Again, the green ones, so these original competition winners are quite good, especially the modified version, but it is still outperformed by last RL in this case. For this problem, if we take, again, the basic version with where we just have the demand to cover and this minimization of the number of shifts, then actually we can solve this to optimality for almost all instances with a network flow-based formulation. But for these extended problems where we have a lot of objectives, this is actually the best approach that we currently have to use these very general methods. And finally, for bus driver scheduling, regarding the feasibility of instances, this is more or less in the middle. So basically, we have a large feasible space that we can move through, but there are also many constraints that make it infeasible easily if we arrange the bus legs in the wrong way. And for these ones, actually, these ILS-based ones do perform very well, like in this academic benchmark, and are the best methods in this comparison. Again, the original competition winner is very good, and also our hyper-heuristic is also among the best ones. What do we use here in practice? So we have this branch and price approach and an LNS based on this branch and price approach, which is clearly the best if we don't change the rules too much. So this is gives us the best results, but it is very hard to adapt. the hyper-heuristics can outperform most meta-heuristic approaches that we have actually. So like simulated annealing and taboo search. But there is one which is CMSA, which is better than these hyper-heuristics on the problem, but still is tuned for the problem, while the hyper-heuristics are basically just applied as they are without any further tuning. So still quite good in this comparison. Now, what we then did in this paper was we also went further inside. So we've now seen these average comparisons, but then we asked, okay, what are the hyper-heuristics actually doing internally? Like we have a lot of different low-level heuristics. Do they go for the same patterns? Do they have actually different patterns, how they combine them? Can we learn something from these? And I'm just showing some very brief glimpses of this, because you can go very deep down and try to find all kinds of patterns down there. But in this case, this is for minimum shift design. And these are the 20 different low-level heuristics that we have for this problem. So the ones that start with an F are first improvement with different neighborhoods and different number of steps. B is a kind of best improvement. A is like an alternating local search where it always tries to remove one shift and replace it by another one. This is a randomized hill climber. Then we have M are the metropolis acceptance criterion mutations, so likely to improve but can also get worse. W is random walk. And then we have these four destroy and repair heuristics. And what's immediately obvious is actually the hyper-heuristics. So here we just show some of the best hyper-heuristics overall. And like all of them here performed well on this problem, with the blue one, which is ours, as the best one. But all of them performed well, but they do completely different things, which is quite interesting. So the ILS-based ones, they really focus on these large-scale local search operators that do some exhaustive search in a large neighborhood, are therefore quite slow, but can also give quite big improvements. They seem to really prefer those. While, for example, this original competition winner, GIHH, goes for randomized hill climbing and those kind of metropolis acceptance criterion. So completely different approach, but in this case, the last RL, so in blue, which is more moderated, so it still shows some preference for these large local search heuristics, but it moderates more and spreads it more evenly also to this randomized approach. And in this case, this was the best approach. And this very randomization-based approach that we see for the green ones was also very good, while the strategy for mainly doing these super expensive operators was not as good. But it's quite interesting to see the very different approaches from the different hyper-heuristics here. And if you look at run times, then we can see that really, so here's the scales are now different. So 80%, 80%, and then only 20% of total runtime this is. So we can see that actually the majority of runtime is spent in just these operators, even for the hyper-heuristics that do not use them very often. So they are really, they can get a lot of improvement, but they are very slow. And so, yeah, if we go back to this, we looked at these graphs for all the different domains and for the different hyper-heuristics. And then we also looked at things like what are consecutive hyper-heuristics, low-level heuristics, because these are the individual ones, but it's also interesting in what combinations they are chosen. And also, does it matter if we remove them? Because maybe something is chosen very rarely, but it still helps to get out of a local optimum. And so in the end, what can we learn from this detailed analysis? So one immediate thing is, okay, if we have some low-level heuristics that are basically almost never chosen or do not show any improvements for the results, we can remove them for further runs on the same domain. Because of course the hyper-heuristics will learn that they're not good, but it still takes some time if we want to learn this again and again for each instance. So we can improve the portfolio this way, but we can also use this if we want to actually have a fine-tuned heuristic for one of the domains. We can run the hyper-heuristics on this simple set of low-level heuristics and then have a look, what are the best ones doing? And can we learn something from that? Like, is the strategy with this randomized search better, or is the strategy with this large scale local search operators better for this problem domain? And then we can actually use this to fine-tune our domain-specific approaches and get a head start from what the hyper-heuristics are doing. And we can also loop this back to the hyper-heuristics, kind of like instead of an instance-based analysis, it's basically like a loop back to the hyper-heuristics, like which hyper-heuristics perform well on which domains, and like what were the combinations they were choosing. And maybe we can see, okay, this hyper-heuristic did not perform so well on this domain because it focused too much on these very long-running operators. So maybe we should do something about this, and thereby have this feedback loop and learn from that. Other directions of learning, we used a very simple approach for the reinforcement learning with this tile coding. What about deep reinforcement learning or some other methods? So this was actually the master thesis that was done by Hannes. And in this setup, it turned out to be quite challenging because we are in this online setting usually. The information we get is very stochastic. We might not have such a large budget of low-level heuristic calls to learn from. So it turned out that if you have a very large budget of low-level heuristic calls, and you want to be competitive based on the same number of low-level heuristic calls, then this can be done. But in the overall runtime, it's not as good because the learning takes longer and it just doesn't pay off runtime wise. Like, you can do better for the same number of low-level heuristic calls, but not for the same runtime. Other directions that would be interesting to explore is you could do some domain-based offline learning. So if you want to solve one domain frequently, then you could learn from a set of training instances and then have already something pre-trained for this particular domain. We had these features from the search state. Maybe you want to expose some domain features and include them in this state representation. And what Hannes also looked at in his thesis was pre-training and transfer learning, which can also show some benefits. So for example, we do this ILS-based exploration, but maybe you can discover some general rules that help for multiple domains without without inducing some structure yourself. Yeah, so to sum up, we've introduced this reinforcement learning based hyper-heuristic, where we use a larger state of features for the search state and this ILS-based exploration. And with this, we can get high quality results also on our industrial benchmarks without any domain knowledge. And this can help us if we have problems that change very fast or new problems where we want solutions fast without tuning a problem-specific method. All right, thank you very much. That's it. I'm looking forward to the questions.